continuing our distillation video, and this is the second part of the video. So as you know, we have so far studied the TXY diagram and also the XY diagram, which are two most important diagrams to understand the distillation topic. Now in this video, the video number 2, we're gonna extend our knowledge and we will move towards more important things. So let's get started. So as you know that we have seen the TXY diagram, yes, the TXY diagram, and you already know that X and Y were the mole fraction, and this is the temperature, and this line I showed you that this is the boiling point curve, okay, but and also it is called as bubble point curve. Okay, so more important thing is this thing. Okay, so you can also call it the boiling point, or also you can call it bubble point. So this is also known as bubble point curve. Okay, so and this line was dew point curve. Okay, and you also know that this is your liquid region, this is your liquid and vapor two-phase region, and this is your vapor region. Okay, so here this is vapor, this is liquid and vapor equilibrium over here, so that you have liquid composition and vapor composition, and this is your liquid region. So now let's get to more advanced version of this, and let's study it in a little bit more detail now. So guys, as you have seen that in this TXY diagram, we had our mixture over here, and when we increase this temperature, we went to this point, end point, where our liquid got in equilibrium with its vapor, and this vapor has the mole fraction given by this point. Okay, so this is let's say end point, and I call it P point. Okay, and this is our mixture. Okay, so it was our initial mixture, and then it got separated into a liquid and a vapor, and if we keep on heating, we saw that we move along this line. So here suppose I assume a point where this is our liquid. Okay, and let's say from this line, okay, at particular temperature we will get our vapor. Okay, and this L and V are the amount of vapor and the amount of liquid. Okay, I'm talking about the actual amounts, so it will be in moles or in the form of mass, but let's say we take it in the moles. Okay, so you have L amount of L moles of liquid and V moles of vapor, and if you extend this line over here, so this is your mixture. Now here comes a very important thing, because you know that this axis is axis of mole fraction. So what is the mole fraction at this point? See, the mole fraction here will be the mole fraction of our initial feed, and which I call suppose ZF. Okay, so the F means feed, and I'm calling the mole fraction as Z. So this is our Z, and over here we have X, and I'm calling here this is as Y, or suppose I can call it, let's say, X1 and Y1. T1 temperature. So at T1 temperature, the liquid has composition X1, vapor has composition Y1, and the mixture you feed that has ZF composition. Okay, so from this now we gonna look at a very important concept, a very important rule, which is called as mixture rule or lever arm rule. So what this rule tells, that's very important, and this rule is very important, not only in this topic, but after that we will learn about the liquid extraction, and in this also this rule will be very helpful. So what this rule says, listen carefully. Okay, so as you can see, we have amount of liquid, amount of vapor, and the amount of initial feed we have, and also we have data about the mole fraction. So the thing is how we can relate all these things. So the rule says that L, okay, so now this rule says that L upon V. So we have L upon V, the amount ratio will be equal to length of this line divided by length of this line. So we have to go opposite. So L is here in the numerator, then you will take the length of this section. Okay, and so let's see how does it work. So what is the length of this section is y1 minus zf, right? So you have to write it like this, L by V. So we have a line. Okay, so what is this? Y1 minus zf is the length of this portion divided by length of this portion, which will be zf minus x1. Yes, this is our mixture rule, that the amount of the liquid and vapor produced will be in the ratio of the length of this opposite section, and these sections are divided by the mixture or the feed. Okay, so you have to extend the feed zf over here, and there will be two sections over here, and with the help of this you can apply this rule. And this rule is very helpful in many situations, and in the exam also. If you are preparing for the GATE exam, then they can ask about this. Here we're gonna start our new topic over here. This is the Raoult's law. Okay, so this law is the equilibrium law. Okay, so what does it tell? You all already know that if we have a mixture, let's say of A and B, and at equilibrium we know that it will produce a vapor. Okay, and in this vapor, what is the pressure of this vapor? What will be the pressure of this vapor? And this pressure will be equal to the PA plus PB. And what is PA plus PB? It is the partial pressure. This is the partial pressure of A plus partial pressure of B, and both if you add you will get the total pressure exerted by the vapor. Okay, and if you have some, let's say, some external pressure PT. Okay, so this is the pressure exerted by the vapor, and this thing is given by the Dalton's law. Okay, so it says that if you have an ideal mixture of more than one component, then the total pressure exerted by the vapor will be equal to the sum of the individual partial pressures. And suppose we have external pressure PT. Okay, so this is the total pressure exerted by the vapor of the two components, and this is the external pressure. Now when the boiling happens, you already know this concept, that boiling happens when the external pressure equals to the pressure exerted by the vapor. Means this pressure means PA plus PB, right? So when this thing happens, means the sum of the partial pressure equal to the external pressure you have applied. When these things equal, the liquid starts boiling, and at the temperature it happens, we call it boiling point. Okay, so is it clear? When the external pressure equals to the total vapor pressure of this mixture of the solution, then the boiling happens. And at the boiling, that means the liquid is in equilibrium with the vapor. Okay, if you allow them for a sufficient time, then they will come into equilibrium. but the important thing over here that the external pressure should be equal to the sum of this individual partial pressure. And this is a very important concept you should remember, because you will encounter such numericals where they will ask you the pressure at which the mixture will boil. Okay, so what they can ask, then they can ask that a mixture having the two components, and they can ask that x a equal to, let's say, 0.9, x b equal to 0.1, and they can ask that to find the bubble point pressure. That means that at which pressure the mixture will boil, and they will give you the temperature, of course. So this kind of question they can ask. So the thing is how we can find out the bubble point pressure, means this pressure, and which pressure is equal to the sum of partial pressures. Now the thing is how to calculate the partial pressure, and here comes the role of this law, Raoult's law. And this law tells us the PA, and it says that this is equal to the mole fraction in the liquid. I'm assuming x, and x represent mole fraction in liquid. XA means of the A. So we have two components, XA means mole fraction of A, and as we have only two components, then the XB will 1 minus XA. Okay, so what does it say? That the PA equal to XA into multiplied by, this is important thing, multiplied by P naught A. And what is this? This is the vapor pressure. Okay, so this, if you multiply this vapor pressure into the mole fraction, then you will get the PA, which is the partial pressure of that component in the vapor. And if you add the both this thing, you will get the bubble point pressure. Okay, for PB also it will be XB into P naught B. That's very simple. So far so good. Okay, that's very simple. You can get the PA just by using this formula. Now the thing is how to calculate the vapor pressure. Okay, so in question they can already give you the vapor pressure, so they can say that okay, this compound has at this temperature, they will mention at this temperature it has this vapor pressure. Then you have to calculate the pressure at which the mixture will boil. Okay, that's the simple. But what if they don't give? So in some question they will not give you the vapor pressure, but they will make use of Antoine equation. So there is one more equation which is very important, and this is called as Antoine equation. The expression of this is something like this: ln of the vapor pressure of some component. Suppose I'm talking about the A. So the expression you have to remember, because this is very important. Ln of the vapor pressure, then A minus B divided by T plus C. Okay, and here the T is this temperature. Okay, this is the vapor pressure which we need for this thing. And what are ABC? So they are just constants. Okay, so here's the equation, and they will give the value of ABC, and from this you can calculate the vapor pressure. And what will be the units of this vapor pressure and the temperature? This thing they will mention in the question. So here we complete our important part, that how this thing work. So again I'm recalling what the points over here you have to remember is that when the external pressure equal to the sum of the PA plus PB, at this point the system will boil, the mixture will boil. And if they ask for the pressure, you have to use this equation. To calculate P and PB, you use the help of Raoult's law, which says that mole fraction times vapor pressure. If the vapor pressure is already in the question given, okay, then well and good, just put it. If they don't give the vapor pressure, then they will give the value of A, B, C, so that you can use the equation and Antoine equation, and with the help of this you can find the vapor pressure and use this. Okay, another more important thing they can ask, what they can ask, that they can give you the value of ABC, and they can ask you that whether the mixture is saturated or subcooled or saturated. This term means that whether it is at its boiling point, whether it's boiling or not, and subcooled, that means it's not boiling yet. Okay, we need to increase its temperature. So how do we know? Okay, so it's very simple. You have to find the Pa plus Pb. If it is less than, suppose the Pa plus Pb is equal to P, okay, as I told you that this is Pa plus Pb is P, so the total vapor pressure is P. If it's less than the external pressure, that means external pressure is high, so it will not let the mixture to boil, so the mixture is subcooled. Okay, it is subcooled. And if it's equal to the external pressure, that means it's saturated, or you can say it's boiling. So this is another important concept they can ask you. So this all about this kind of vapor pressure and all this stuff. So these two equations were very important, and you should get the idea about this. So let's get next. Now on we gonna study the new term over here, which is very important, called as relative volatility. It is defined by alpha. We call it alpha AB. So as the name suggests, it is relative, means it's the volatility of A with respect to B. So it shows us that how A is more volatile with respect to B. So higher value of alpha, that means A is very highly volatile than B. If the alpha is low, that means that A and B are almost equally volatile, so it's hard to do the distillation. Okay, so that's why this term is important. First, let us see how does it define. So let's have this term A plus B. Okay, here we are assuming that our A is more volatile. So how it's defined? Alpha AB, the relative volatility, is defined by, I'm gonna state the formula first, because the formula is very important. Remember this, y by x. Okay, once you have to write y by x, then you multiply it by 1 minus x divided by 1 minus y. That's how it's defined. So actually it is defined as k value of A divided by k value of B. This is called as k value, and what is k value is nothing but the y by x. Y of A divided by y of x, y of B divided by x of B. Okay, so it's y of A divided by x of A, of course. What is x? Mole fraction in liquid phase of A. xB is mole fraction of B in the liquid phase. Okay, I mean, you have got what I'm gonna say. So xB is nothing but 1 minus x A, of course, and I'm using x as only x over here. So the important thing is this formula, you have to remember this. Okay, so what they can ask, that they can ask for only this thing, or what they can say, that they can give you this value of the relative volatility, and then they can give you x, then they can ask you the value of y. So if you solve this, there is another formula which we get from here, and which is very important, guys. You have to remember this anyhow. Y equal to alpha x divided by 1 plus alpha minus 1x, and this formula is very important. I'll give it 3 star, because this formula is very important. What they give you, they gave you the value of alpha, so they can give you that I have we have a mixture which is alpha equal to 1.25 and this and find the value of y, and they give you x. So when they give you such thing, when they give you the value of real alpha, the relative volatility, it should strike in your mind that we have to use this formula. This formula you have to remember how this come from this equation, and how it is defined from this formula. That's it. It's and now things that what does it mean? So if alpha is greater than 1, that means our A is more volatile. Of course it's alpha AB, and more the value, like if it's 2.45, then it's easy to distillate, easy, because alpha is very much is 2.45 times volatile than the B. Okay, but what if its value is only about 1.05 some? That means this very hard to distillate. It's gonna be very hard because both A and B are almost equally volatile. So here you can see what the term means. This is relative volatility. More the value of alpha than 1, as the alpha value gets higher, it's easy for us to do the distillation, and from higher, that means higher than 1. Okay, so I hope that you understand this thing, that alpha value higher than 1, it's easy to distillate. If it's around 1, then it's very hard to distillate, and it's then we have to use another methods, like the liquid extraction, if the value is very much close to 1, and it happens in the case of isomers and all that, where the shape and size are almost same. That's why the boiling point of both the components are equal, almost equal. That means alpha is equal to 1 almost. In this case we cannot separation, we cannot separate actually.